All right, so I want to talk briefly about the tangent that we know from SOHCAHTOA, opposite divided by adjacent, right? And the tangent that we talk about today. Because today, when we talk about a tangent today, we're talking about a shape. But I want you to see that there is a direct connection between what we've talked about with trigonometry and what we talk about today. Why the name, even though it might not seem like they are connected, why the names are the same for the ratio of opposite and adjacent in this segment or line that we're going to talk about today. Okay? So a tangent, okay, the way I remember this, the word tangible means what? Able to touch. This desk is tangible. Okay, I can touch it. All right. My IQ is not tangible. You can't touch somebody's intellect, right? Does that make sense? Okay. Your leadership, that's an intangible characteristic. Okay. Your work ethic is an intangible. Does that kind of make sense? Things that you cannot touch. So if I know what tangible means, then I can make it maybe an extension and understand what tangent means. Tangent in mathematics, if we're not talking about SOHCAHTOA, tangent refers to a segment or a line touching a curve, and for right now we're going to talk about that curve being a circle, one time, and only one time. Okay? A tangent to a circle is a line in the plane of the circle. That phrase is key, in the plane of the circle, that intersects the circle in exactly one point. Okay? The way I like to think about it is if I were to take like a dinner plate and a ruler or something like that, piece of string, yardstick, whatever it may be, so here's my circles, obviously my dinner plate. This line here is my ruler. If I push them up, they're going to touch one time, right? This line is said to be tangent to that circle. Okay, we call this a tangent line. Does that make sense, everybody? Okay. Now, we can create every circle has a bunch of tangent lines. Okay, so here are all the tangent lines that go through maybe B on this circle as I move B. Okay, but they only touch one time. Does that make sense, everybody? Okay. They have to be in the same plane. So what we mean by that is if I look at, delete that, let's go to 3D here. Okay, that line touches that circle one time. Do you agree with that? Touches that circle at B one time. But that line is not in the same plane as the circle, so that is not considered a tangent line. Okay? That line as well would not be considered a tangent line. Okay? Depending on how this line intersects. Some people ask, well, if it's not a tangent line, what's it called? Right now, I've got that thing intersecting at a right angle down here. Maybe I don't. Maybe there. If this is a right angle down here at the bottom where it does intersect, we would say that line is maybe normal to this circle or orthogonal, but it would not be a tangent. Does that make sense? Okay, they have to be in the same plane. We would have to have something, again, like we saw over here. Yes, Connor? Okay, so you're saying something like like that. Okay, so that would not be a tangent, okay, because we can have portions of lines being tangent. So I can have, let's see here, let's say that I've got this. All right, so we can have segments that are considered tangents. That'd be a tangent segment. Or we could have rays. So if I went from like B straight through H, and I looked at that ray, that would be a tangent ray. And the reason those would be tangents is because if I make it into if I extend this ray into its full line, it only intersects that circle at that one spot, right, at B. Where if we go back to that picture there, looking at this red line, if I were to extend that red line, because right now it's only a ray, but if I were to extend it in its entirety, does that one now cross the circle twice? Okay, so we want to look at the idea that if we're looking at just a ray or a segment, if we extend it to the line that it came from, does that line intersect the circle more than once? And if it does, it's no longer called a tangent. What that line is actually called, though, is a secant. You guys remember talking about secants in trigonometry? Secant being the reciprocal of cosine. That's what we call that, a line that goes through a circle or curve 2 times. A calculus concept that we're interested in, just so you guys can see where this would maybe extend to beyond this class. How many of you are freshmen in here? Okay, so freshmen, you are on track to take calculus. And in calculus, what we're interested in, let's say I have, we'll go fit poly between A, B, C, and D. What I'd be interested in calculus is what is the slope of that curve no matter where I'm standing, okay? Because we talk about slope with lines, right? What's the main feature you know about slopes for a line? And no matter where I stand on the line, what is the slope in comparison to anywhere else I stand on the line? Say again? Okay. Let's take that a little bit further. So if I take, because I agree with that to an extent, let's say this is my line. If you are standing right here, where my cursor is on my line, you have the same distance as a ratio to go off that line to get back on it, no matter where you're at, right? Okay? So even if so there I went up like 3 and over however many. But even if I go up just a little bit and over a little bit, that ratio of those 2 distances is always going to be the same. Does that make sense to everybody? Okay? So if I look at it this way, like that distance compared to that distance as a fraction is the same as maybe that distance compared to that distance as a fraction. Slope on a line is constant. That's the relationship, okay? And that's the idea. Like if you're standing here, if you're standing at point G, are you experiencing the same kind of incline that somebody at point F would be experiencing? Does that make sense? Okay. Well, let's look at this curve. If you're standing at point A, okay, and we're moving right or left to right. So if you're standing at point A, you'd be kind of going down, right? You got a severe slope going down. Somebody that's standing at point C has more of it's less severe, but they're pointing up now, aren't they? So the slope on a curve like this is always changing. Okay, it's different depending on where you're standing. So what we do is we So if I want to know the slope at, let's say, we'll use M as the point here, make it red. If I want to know the slope at M, what we do is we find a tangent line to the curve at M, okay? And whatever the slope of that tangent line right there at M is the slope of the curve at M. Does that make sense? So I'm standing right on M. I'm at the same spot on the line as I am on the curve. So that slope would be steep. The slope right here would be 0, right? Or close to 0, okay? Positive slope for this curve, there'd be 0. There'd be a negative slope for this curve, okay? And that idea of tangent, what we're showing you right there with that curve, is calculus. And we'll use calculus later on to determine what is the slope of M, because it's different everywhere M goes. Okay, and we'll develop formulas and equations that allow us to find that quickly. And that's what calculus is about. But the extension of geometry, talking about tangents right now, the reason I introduced this is so that you can say, okay, I'm going to be in that calculus class in 2 years, 3 years, whatever it may be. I should probably know what tangents are. Okay. The point that the tangent line touches your circle or touches your curve is what we call the point of tangency. Okay, point of tangency. We cool with that? All right, I'm going to show you the relationship between what we know from trigonometry to what we talked about, tangent with the opposite divided by adjacent, right? SOHCAHTOA, opposite divided by adjacent for tangent, and the relationship of what we're talking about right now. In geometry, we can construct a right triangle, all right, and then we start talking about trig, and I compare that side right there with that side right there, the blue side compared to the purple side of that right triangle. If I do that through division, that is what we refer to as the ratio that is defined as tangent, right? Okay, the blue one divided by the purple one. Okay. Every single triangle in the coordinate plane, okay, the hypotenuse is considered a radius, okay? If I keep this hypotenuse, so this hypotenuse right now is a length of 1, okay? If I keep my hypotenuse as a length of 1 and rotate that around so that I create a circle, that is the circle that I get. Does that make sense to everybody? Okay. So basically this circle here is defined off the length of my hypotenuse. That's 1. I can make my hypotenuse 2, I can make it 3, I can make it 4, whatever. Okay. It makes most sense in trigonometry to make it 1. Okay. Because think about sine. Sine is opposite divided by hypotenuse, right? Well, what number would you always like to divide by if you had the option? What's the easiest number ever to divide by? 1. Okay? So if I can make this hypotenuse 1, that makes the sine just this blue distance. It makes the cosine just this purple distance because it's all going to be divided by 1. Does that make sense? Okay? So where does tangent come from? Well, tangent, and how do these names relate to each other? Tangent is the blue segment divided by the purple one. So I'm going to take, and I've already got it here somewhere, but I think it's that one. But I'm going to take CD, the blue side, divided by AD, the purple side, hit enter, and it gives me that number right there. Is that okay with everybody? Okay. Now, what I'm going to do is I'm going to insert a line here that goes through point C and is tangent to this circle. Not that line, it's that one. Would you guys agree that based off our definition of tangent, that is a tangent line, right? Okay. I'm going to look at the distance that is from C to E here. Okay, it's a distance of that is on that tangent, a portion of that tangent line that goes from that point of intersection on my point of tangency to the x-axis. And if I look at that distance, it is that distance right there. Okay? And if I ask it to tell me that distance, it's 0.9425. It is the same. That red distance right there is identical, no matter where C goes, is identical to that distance divided by that distance. Does that kind of make sense? And because that number right there and then this quotient are identical, because that red portion is part of this bigger line, we call that line a tangent line because of this tangent ratio. Does that make sense? As I move C, okay, that length is 1.774. If I divide blue by purple, still getting 1.774, or 17774. That kind of makes sense? Okay, so that's the, when we're in a unit circle, that's what this is. It's with the radius 1. That is your sine. That distance right there is your sine. That distance right there is your cosine. That distance right there is your tangent. And that's a direct link then to SOHCAHTOA and the tangents that we talk about right now. In the past, people would ask, when I had 4 classes of geometry, I wouldn't spend a whole lot of time talking about that, but since we only got 1 class, I don't have to keep everybody on the same pace. People would always ask, well, is this the same tangent as we've talked about in the past? And I would say, yeah, they're linked, but don't worry about it, okay? I think it's important to see that. I think terminology-wise, I think it's a benefit to realize that they are indeed exactly the same thing, okay? When we look, what are the properties for tangent lines? That is very informative, very useful. And this is what this is the reason I want to talk about this today, because the end of course exam has shown this or used this previously. If I take a circle, okay, so here's my circle, and what would you call that segment right there for my circle? A radius, right? Okay, let's draw the tangent line. So there's my tangent line. Okay. So I got my red radius, got my blue tangent line. Anybody want to take a stab at what they are doing to one another when they intersect, or how they intersect? They're perpendicular. Okay? And we can see, I can ask this to determine what is the angle between the blue and the red. Now it puts it on the outside for whatever reason. But that is a 90-degree angle there. Does that make sense? Now as I move B around and I change the circle, does it matter how big the circle is or where that radius is? No. Okay? So what we have here is a theorem that says if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. Okay. If a line is tangent to a circle, then it is going to be perpendicular to the radius at that point of tangency. I think that's kind of wordy. The way I remember is if I've got a radius and I've got a tangent line, they are going to be, at the point of tangency, they're going to be perpendicular all the time. Okay? And there's actually a converse to that. Okay? So this says that the radius is perpendicular to the tangent line at the point of tangency. If you were ever to find a radius and some line out here that were perpendicular, okay, then you would know that that line indeed is a tangent line. But that theorem allows them to ask questions like this. Okay, they're going to ask you what is the value of x. There's a couple different things that have to play into this question. Obviously, one from this relationship that we just talked about. If I look at that right there, and LM. And what they'll say in your homework a lot of times is, if it looks like a tangent, then it is a tangent. Obviously, because of the way that our pixels work when we're constructing something, this looks like it intersects that circle a lot more places than just one, right? If I zoom in on it like that, they're going to say, if it looks like a tangent, assume that it is a tangent. So this looks like a tangent, that looks like a tangent. So we're going to assume that they are. So what kind of angle would be here at L? Be a right angle, wouldn't it? That's a radius, and that's a tangent. They meet at a right angle. What kind of angle is going to be here at N? Right angle again, right? How many degrees are there in this shape right here? Or what would you classify, based on the number of sides, what do you classify that shape as? Say again? Quadrilateral. Quadrilateral is how many internal degrees? That, right? And N is 4, so we have 4 minus 2 is just 2, times 180. Doesn't have 360 degrees? How many degrees have we chewed up with these three angles here? Minus 117, minus 90, minus 90. Can we do that? Will that give me what X is? Okay, so it turned out to be 360 minus 180 minus 117, 63. Is that all right? Okay. What we would also find out about this particular image is that this is actually, this blue shape is actually a kite. Okay. Let's figure out what X is there. X, what they're talking about here, and you'll see this in your homework because their pictures they draw too small. It'd be hard to determine what they're asking X to be. X is angle E here. See if you guys come up with angle E's measurement. Angle there. So really what we're looking at here, so they're basically giving you this circle information so that you can learn something about this triangle, right? So it's a triangle question, but they're hiding information about that triangle through the knowledge of circles. So we got 90 plus 38, that's 128, right? So doesn't this angle here, X, have to be 62? No, 52. I'm not very good at math. 52? You have to add up to 180, right? This question a lot of times gets people confused. Okay, and I've seen similar things like this on the end of course exam. What kind of triangle do we have there? The right triangle, correct? They might not always, they're at angle B. I put in the red square to show the right aspect of it, or the right angle aspect of it, but they don't always do that. They might just say AB is a tangent line, and CB is a radius, so you need to know that that ends up being a right angle. But how can I find X? Okay, so which angle is 30? Okay, so which angle, how do you know it's 45? I can do the Pythagorean theorem. Going off the angle question, they don't tell me anything about this angle here or that one. So I don't want to make the assumption that it's 30, 60 or 45, 45, because it could be 10 and 80. It could be 20 and 70. But we know that this is X and this is 12, right? What is this? It's the hypotenuse. And what would you identify it as algebraically? X plus 8. So then could I say x squared plus 12 squared equals x plus 8 squared? And here's what I don't like so much about the end of course exam. The ACT does the same thing, is that they will deliberately write questions like this to make you square a binomial. They want you to square x plus 8. Because everybody's going to get this right. Everybody's going to go x squared plus 144. And then everybody that gets this wrong is going to write this as x squared plus 64. And they get down, they either get it wrong or they get confused because in this case, the x squareds will cancel out. I get 144 equals 64, and they don't know what that means. That's a false statement. What am I missing here? What does x plus 8 squared really mean? X plus 8 times itself, right? And when you have a binomial times a binomial, how do you expand that? You distribute, and you distribute twice. So for us, it'd be that FOIL phrase that we talked about, right? So what I'm missing here is the O and the I. 8 times X. And then 8 times X again. So it gives me 16 X's in the middle. And they do that intentionally because a lot of people will take x plus 8 squared and rewrite it as x squared plus 64. Does that make sense? Okay. And usually what they'll do, for whatever reason, like they'll make it like a 2x squared here. So that the x squareds don't disappear, and you would end up being able to solve and get an x value, and one of your options then would be that incorrect answer. So they mess with you, making you think you did the right thing. Does that make sense? Because one of the options is that wrong answer. So just be on the lookout for that. The nice thing about this question, though, here is the x squareds shouldn't end up canceling each other out, right? I can subtract 64 from both sides, and we get 18 equals 16x. Or sorry, 80. I don't know why I said 18. 80 equals 16x. If I divide by 16, does that give me 5? And if you know anything about Pythagorean triples, 5, 12, and that side has to then be 13 if that's the case. Again, dealing with that's a concept, Pythagorean theorem, concept from chapter 8. We're in chapter 12 now. Okay? So we're really doing the same thing we did in chapter 8, but in order to know that I used the Pythagorean theorem, I need to use this property that they established in chapter 12, about tangent lines being perpendicular to radii at points of tangency. Another example of the same thing. Okay, so here's kind of the converse of that. I don't know if these are tangent. I have no idea. But if they are tangent, what kind of angle would you have at angle L? You'd have a right angle. So if these are tangent, then this would be a right triangle. Does that make sense? So could I say 7 squared plus 24 squared? How does that relate? Does it equal 25 squared? So 7 squared is 49. 24 squared is 576. And 25 squared is 625. When I add those together on the left-hand side, do I get 625? Yes, I get a true statement right there. Okay, 625 does equal 625. So that confirms that the Pythagorean theorem, we talk about the Pythagorean identities in trig, the Pythagorean theorem is true here, so that must be a right angle. So if that is a right angle and that is a radius, this must be a line of tangency, or tangent line. Is that all right? Okay. As we move through, there's some other vocabulary words and concepts that exist. Let's talk about this real quick. I want to demonstrate this without that static picture. It's kind of boring, the static picture. If we have a circle of any size, okay, and we take a point that is outside that circle, so point C, okay? What I'm going to do is I'm going to take point C, and from it, I'm going to draw a tangent line to that circle, okay? So we should be able to see that set of tangent lines. There's two of them you can draw. One to the bottom of the circle, one to the top of it. Does that make sense? Okay. I'm going to ask GeoGebra to find those points of tangency, point D and point E. And what the theorem is saying is that distance and that distance are the same. Okay? So if you create a circle or construct a circle, and then from a point that is not on that circle, you draw two tangent lines to the circle. Okay? And I can move this around and show you that there's always going to be, no matter where point C is, there's always going to be two tangent lines. Is that okay with everybody? It is telling you that that distance there and that distance there, they are always 100% of the time going to be the same length. Does anybody know why? What if I did this? What kind of angle do I have right there? I have a 90-degree angle, right? Let's do this. What do you have there? 90-degree angle. Okay? Do that. Okay, now you have two triangles, don't you? Okay? Now, let's just talk about this distance here. What is this distance A to D? What do we call that for a circle? It's a radius, right? Okay. Is this a radius as well? What do you know about two radii that come from the same circle? They're congruent. They're the same thing, right? You know those are right angles, yes? Okay. Is this hypotenuse, AC, is it part of both these triangles? If I call that triangle 1 and I call that triangle 2, are triangle 1, or is triangle 1 congruent to triangle 2 by hypotenuse leg? Remember talking about that back in chapter 4? If you have two right triangles and they have a hypotenuse and a leg congruent, and that's what we have here, then the two triangles are congruent. Okay? Well, would that segment right there be corresponding to that segment right there? So then those red distances are congruent by CP/CTC. So if you remember back to chapter 4, we talked about how everything we were learning in chapter 4 sets the stage for being able to learn new facts about new shapes. And I said one of those shapes that we're going to learn things about is circles. And people are like, well, that makes no sense. How a triangle is going to tell us stuff about circles? That's a triangle, or sets of triangles telling us something about this circle. Is it okay with everybody? So that's what that theorem says. If two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent. Okay. We've talked about this before. These are just inscribed and circumscribed. It's always, inscribed means on the inside, right? Circumscribed, circum means on the outside. So if I look at those two images, I'm going to talk about them in two different ways. I can say there's an inscribed circle or a circumscribed triangle. Does that make sense? Or polygon. Okay. When we do that, when we talk about things that are circumscribed or inscribed, however we're referring to it, if the polygon is circumscribed, a condition on circumscribed means that all the sides of the polygon have to be tangent to the circle. So if I've got a triangle being circumscribed around the circle, then we have a point of tangency there, point of tangency there, and a point of tangency there. Does that make sense? All sides have to be tangent. So if I were to give you maybe all right, so if I gave you I want to give me that. There we go. A polygon like that, okay, is that considered circumscribed around the circle? No, okay, because it's only tangent on 2 of the 4 sides of the polygon, right? Now, if I did this, made that side tangent, it's still not circumscribed. The polygon is not circumscribed, and the circle is not inscribed. But maybe once I do that, now they are. Does that make sense? So the conditions about being circumscribed or inscribed is not just being on the inside and not just being on the outside, but you got to have tangency on all segments in order for those characteristics to exist. Okay. We talk a lot, I'm going to skip over a couple of these. We talk a lot about lines being tangent to circles, but we can actually have circles being tangent to circles. We can have lines being tangent to multiple circles. Okay. Here we have what we call a common tangent. A common tangent is a line that is coplanar with 2 circles and is tangent to both circles. Okay? So here's a situation. This is actually referred to as an external common tangent. Okay, because it's on the outside of both circles, and we'll talk about how we can identify that here in a moment. But that's an external common tangent. There's another one for that picture. Would you guys agree that there'd be a tangent down here as well? Okay. Now, what I want you to see, a real-life application of this, you guys ever seen, so this portion here would be our tangents. We've got something going around this portion of this circle, and we get another external tangent there, and it comes back around here. What did you say? A belt for what? Okay, so it looks like a serpentine belt for a car, or a chain on your bicycle, right? Does that kind of make sense? Okay, wrapped around the gears. Our knowledge about those lengths and those distances allows us to understand and do mathematics with gears, gear ratios, and that kind of stuff, okay? But these are external common tangents, okay? Same thing here. It's just now the circles have been moved together. You can still have 2 common tangents. You can have one coming down through here. But now if my circles look like this, can I draw another tangent that intersects both those? If I draw a tangent to this one, it intersects the bigger one twice, right? So it's not a tangent to the bigger one. If I draw this tangent, it's a tangent to the bigger one, but it comes nowhere close to touching the smaller one. So there are no other external tangents I can draw here. There's only one when these circles touch like this. Okay? Is that okay with everybody? This is referred to as an internal tangent, and there's two of them. Okay, so every set of two circles has two external tangents, and we'll have two internal tangents. The way we talk about internal tangents, the definition is if you were to connect the centers of your circles, if you were to connect those centers with an imaginary line, an internal tangent will cross that imaginary line. An external tangent will not cross that imaginary line. Okay? So if I look here and make that imaginary line right there, does the external tangent cross it? No. Okay? So that's how we decipher internal or external. Now, why do we talk about this? There's a situation so this is if you go through the notes, if you print them out, that's just the static pictures of defining internal and external tangents. Circles, and we saw one of these pictures previously, but that one on the left. Circles, if there is one external tangent that can be made, and only one external tangent that can be made with two circles, we then say that those two circles are internally tangent to one another. So it's a circle being tangent to a circle. Okay? It's the idea of, I use the dinner plate idea. If I have a dinner plate and a saucer plate, I can put them both internally touching each other at one point on the outside of the rim of those plates. Does that make sense? Okay? This is internally tangent. If you can only draw one internal tangent between two circles. So here is one internal tangent. You agree I can't draw another one? Okay. If that's the case, then you've got what we call two externally tangent circles. Means that the circles are outside one another. Okay. But they're touching. This is the dinner plates on my desk, just mushed together. Okay. Not overlapping, just touching at one point. It's kind of like if I were to make, we could do this with like snowmen. If I was to make perfect spheres for a snowman and set the bottom or the base on the midsection, they should be touching at one physical point, right? And those would be externally tangent spheres. So we can extend this stuff to spheres and other shapes as well. But internally tangent means the circles are on the inside of each other. Externally tangent means they're on the outside of each other. Is that okay with everybody? Anybody have questions on tangents? We cool with that? And your homework is just going to basically be a couple questions that ask you to maybe identify internally external tangents, questions that might ask you to do some of this stuff where we have to understand the distance from P to X is the same as P to Z. The distance from R to Z is the same as R to Y. Q to X is the same as Q to Y because of this theorem right here. Yeah, you might see some of these questions up here that we talked about. You will see this question in your homework. When they say X here, this has always been, and this is because they draw their pictures too small, it's always been a question, well, what do they mean by X? Is X this angle right here, or is X this angle? Okay? They want X in your homework to be that angle right there. Is that all right? But it'll be this exact same picture. 60 is that angle right there. Okay, so we'll see that in your homework. I anticipate maybe having to talk about that one tomorrow. But I'll open 12.1.